Okay, hello everyone. Welcome to Data 8, Lecture 16. Today we're going to be talking about statistics. It is a beautiful Friday morning. The sun is shining, birds are chirping. What better day to learn about data science? All right, so I have some announcements. So if you have a conflict for your final, today is the last day to email me, okay? So our final, again, is on the last week of class on Thursday, August 10th, from 2 to 5 p.m. If you have a final conflict with this class, you need to let me know by 5 p.m. today. Send me an email. Another reminder that we're taking interest in having a tutoring session specifically for coding. So if you're having trouble specifically with the coding part of this class, please go ahead and fill out that form. The link is in our announcement section on the course webpage. Fill it out, and we'll use that to gauge interest as to whether we would like to do something especially for you or not. Homework 4 was released yesterday, and it is due Tuesday of next week. Project 1 is also due tonight, so if you haven't started, now's a great time to start. Or after this lecture is a great time to start. Finally, we have a midterm next week. It'll be held Friday in class from 10 to 12 p.m. Okay? The location is still to be determined, but it will be held at that time. We'll let you guys know the details as it comes. Any questions? Yes?
Is midterm going to be like written, or is it going to be all in Python?
Is midterm going to be written or in Python? It will be all written. Okay. So there will be coding questions. You won't have to write that much code, perhaps only filling in a couple of blanks or writing a couple lines. So don't worry about writing like tons and tons of code. But it will be all pencil and paper, okay? So no computers. Okay. Yes, Kevin?
I noticed something about, can I ask something about homework submissions right now, or should I wait until later?
Is it something that you think the whole class will benefit from hearing?
I'm not sure.
Okay, then.
I don't know about other people's problems.
Okay, then ask me after class. Okay, so to kind of recap what we've done the past couple of days, we've looked at probability. So I pulled out some cards out of my hand. We talked about probability. And then we talked about simulation, right? So we looked at the Monty Hall problem. And we simulated that. And we looked at, oh, OK, like probability, the rules of probability say it's better to switch. But let's see whether it happens in real life or not. And we simulated that. And we got back, it is indeed better to switch. Okay, let me show you one more example. So if you recall from yesterday, we were looking at dice. Okay, so we took a roll of the dice. Let me open up my notebook. We took a dice, and we said, OK, the probability histogram of getting each face on the dice is 1/6, right? Because there's 1/6 chance of getting each face if I roll the dice. However, I can also simulate rolling the dice. And as I simulate and I increase my sample size, I noticed that the empirical histogram starts to look more and more like the probability histogram. Okay, so the reality starts to match the theory. So now today, I'm going to look at a real data set. I'm going to look at the delays in flight times from United Airlines. Okay, so I have here a data set with the date of the flight number, destination, and how long the delay was. And this is in minutes. Okay, so this particular plane was like 4 hours late. This particular plane was 30 minutes late. This particular plane was 3 minutes early. Okay, so there's some early planes. Let's take a look at the distribution of these planes. I can do hist and delay. Go. So you get this. It's not really super clear what's in there, so let's use the bins and figure out what's in there. Okay, so delay, and I'm going to do bins. So that means that there are some planes that were like, I don't know, really, really late because the histogram stretches all the way out here. I'm just going to cut them off because I'm only interested in like this range right here. Okay, so let's do from -20 to 300, incrementing by 10. So there we have this. And now if I pass in another argument called units, I can make this histogram look a little bit nicer. So before it was just delay, now it's delay in minutes. And then here's percent per minute. Okay, so here I have this histogram. If you look at this histogram, you see that most of the flights are not late or a little bit early. So it turns out that United Airlines is pretty good at getting you to the hospital on time for these particular flights. Maybe not so much for these guys. Okay, so let me ask you a question as a warm-up. What proportion of flights were between 10 and 20 minutes late? Okay. Go ahead and try to figure out what it is from histogram. Talk to your neighbor about it. Go. Okay, so between 10 and 20 minutes late, what proportion? Okay, so if you recall, when I'm looking at a histogram, when I'm trying to find out the proportion in between a bin or the proportion of items in a bin, I want to find out the area of that bar, right? So if I look at this bar right here, it looks like the bins are every 10. Sorry, it's not super clear here where these are because there's like no gap in between bars here. But if you look, this is 0 and this is 0 to 10, and then 10 to 20 because I'm using bins that increment by 10, right? So this is 0 to 10, 10 to 20, 20 to 30. So this right here is a bar that I want to look at. Let me make this a little bit bigger. There we go. Okay, so right here, it looks like the height of this bar is a little bit over 1, and the width of this bar is 10 because I'm looking at the bin from 10 to 20. So the proportion of planes that fall inside this bar right here is 10 times 1-ish, so about 10%, probably a little bit over 10%. Okay. I can verify this is the case by looking at my United table. I'm taking only the planes that have delays between 10 and 20 minutes. So where delay are between 10 and 20. So now I have only these planes. So if I take the number of planes here and divide it by the number of planes overall, I get the proportion of planes that were between 10 and 20 minutes late. So here I'm going to take the num rows, and divide it by the entire table's num rows. That's getting cut off. I'm going to wrap it in parentheses. That, that. Okay. And I see here that indeed I do get about 10%, 10.5%-ish. Okay. Any questions about that? All right, excellent. So what I'm going to do now is I'm going to say, OK, well, in this original table, I had a lot of rows. Right here are like 14,000 flights. Maybe I don't want to look at all of them, or maybe I only have access to some of them. Maybe I want to sample some of the original table to work with, so I don't have to work with all 14,000 rows. Okay, so what I'm going to do is I'm going to do United.sample 100. If you recall, .sample takes every single row in my table and draws them at random. It turns out that sample draws them with replacement. In this case, if I take a sample of 100 and then histogram them like before, so I'm just going to sample it and then histogram it. So all I did was call .sample before calling .hist. So it's kind of long, but sample and then hist. And you can see here that my sample of size 100 looks like this. Okay. So it does have most of the shape of the original. It looks like maybe this got mangled up right here, but it's a relatively small sample, and my population of flights is pretty big. Okay, so here's what a sample of size 100 looks like. Yes, Kevin?
Is there ever a limit as to how big a sample can be, like 10% of the population? Or what?
Is there ever a limit as to how big my sample can be? Well, I'm going to try it out. So maybe I can go, so here's 1,000. So it starts to look more smooth. Maybe I go 10,000. What if I do 100,000? My original table had 14,000 rows, right? So this is way beyond my original table. If I actually take a sample this big, it will be perfectly fine. And that's because samples with replacement, right? So each time it draws, so it's going to draw 100,000 rows from my original table. But it's just going to look at my whole table, pick one row at random, look at the next, and look at the table again, pick one row at random, do that 100,000 times. It has no problems doing that. However, I would have problems if I asked it to sample with replacement, right? If I asked it to sample, without replacement, with replacement equals false, I believe it will complain about that, because if you're not sampling with replacements, if you're trying to take out 100,000 rows from my original 14,000, then at some point, if you don't replace the rows back into the table, you're going to run out of rows. Okay, so by default, you can sample as big or as small as you want. That's because it's sampling with replacement. Okay, so you notice something kind of interesting about this, right? So as I go from a sample of size 10, right, which looks nothing like my original, to a sample of size 100, a sample of size 1,000, it looks more and more like my original distribution. Okay, and that's an important fact that we discovered yesterday called the law of large numbers. Okay, so what I can do for you now is let's take this and let's put it into a function. But maybe I don't want to. Maybe I want to specify how much I want to sample, and I'll have to retype this and change it every time. Okay, so you notice me having to manually edit the code, like 10,000, 1,000, 100. I have to change that code and rerun it every time. Maybe I don't want to do that. Okay, so here I'm going to define a function called united sample and hist. And instead of specifying 1,000, I'm going to pass an n. Okay, just like that. And now I can just do united sample and hist with 1,000, with 100. Okay, so same thing as before. When I define a function like this, I talked before about using interact. Okay, and it turns out that in this case, I can use interact to do that. So this is one convenient thing about putting your stuff in functions. So if I use underscore equals interact, united sample and hist, and I say n is equal to 1,000, I get this, and I can just slide this around to change the value of n. Okay. Now it turns out that when I do this, you're gonna notice that if I do that, I get 2 histograms. Okay. If I do that, I get a third histogram. So I keep getting histograms that get stacked below here. If you actually want to make sure there's only one histogram, one little thing you have to do is make sure to put plt.show here. That kind of tells Python to clear out my old histogram and then make a new one. Okay, so I'm going to do that. Now I can drag the slider around. Bam. Okay, so I'm going to increase n, and it looks more and more like a population. I can also decrease n. Oh, can't go negative. Okay, so maybe not negative, but maybe 580. I can also change it here, maybe to 10. Okay. A nifty little trick. If you happen to have something you're changing a lot, you can just stick it into a function and then call interact on it, and that'll give you some interactive elements. Yeah.
Why are they negative?
Yeah, so by default, Python just says, oh, this looks like a number. So I'm just going to give you a slider that lets you slide between numbers. And sometimes the slider can go negative, which is unfortunate. If you actually want to limit your choices, what you can do is instead of passing a number here, you can pass in an array of numbers. Okay, so if I do make array, and I do 100, 1,000, 10,000, instead of getting like a slider, I get a drop-down menu, and I can just select from here. Okay, so that's one way to limit your choices if the defaults are not super smart. Yeah, Kevin?
When you move the slider, is it taking a new random sample each time?
That's right. So each time I move that slider, it's actually just calling united sample and hist with the number that was in there. Maybe it was 2, 3, 4, 5. If I move it again, then it'll call it again with, like, say, 1,000. So each time I move it, it's just going to call it. It's just a shortcut to calling it myself. But I could have just called it myself every time. Okay, cool. All right. So I have a question for you. I roll a die 4 times. What's the probability that I get at least 1/6? Okay, so go ahead and talk to your neighbor about it. Go.
The probability of getting no sixes, you do 1 minus 1/6 to the power of 4. No. 5/6 to the power of 4. Yeah. I saw my answer and missed it. I don't know why. My answer comes in ellipses.
Okay, so I heard a lot of 1 minus, kind of 1 minus here, 1 minus here. Yeah, right idea, right? So in this case, it's easier to calculate the probability of the opposite, right? So the probability of getting no 6s and then doing 1 minus that to get the probability of getting at least 1/6. So the way to do that is to take the probability of getting no 6s. So that means I rolled not a 6, and then I rolled not a 6, and then I rolled not a 6, and then I rolled not a 6. And then I do 1 minus that, and I get the probability is about 52%. Okay. I needed to sneeze, but I don't need to anymore. Okay. So, but what if I wanted to look at the probability of getting 1/6 if I roll a die, let's say 5 times? I could add another 5, 6 here, right? But this seems kind of clunky. I'm like changing the code. It's requiring me a lot of manual work. I can simplify this expression first. So I can take that and say, OK, well, here I'm just taking 5, 6 to the power of 4. So I'm going to do that to the power of 4. So these two things are the same. And then I can say, well, instead of using 4 here, I can make a variable called, let's say I want the number of rolls to be 5. And I can do 5, 6 to the power of 5, or to the power of rolls. And that will, I can just change rolls now and get back different values for how likely it is to get at least 1/6 if I increase the number of rolls, right? So if I take a die, roll it a bunch of times, the more times I roll it, chances are I'm going to get a 6, right? So I should expect that if I increase rolls, it's going to go closer and closer to 1. Let's see how that actually happens. So one nice thing about doing mathematical statements like this is I can do it on individual numbers, or I can just do it on an array, right? So if I take np.arange, and let's say this goes from 1 to 51, now I have a bunch of probabilities, right? I just calculated the probability of getting at least 1/6 depending for a bunch of rolls. Okay, so I have a bunch of rolls here. This is kind of hard to read, so let me put it into a table and then plot it. Okay, so I'm going to take that and put it into a table. So let's call this table at least one table with columns. And I'm going to say my first column is my rolls. Second column is the chance of getting at least 1/6. And I'm going to say that is just this guy right here. Stick that into my table. Now I have a table. So I just took my result, put it into a table. Now I have, OK, if I roll a die once, the chance of getting at least 1/6 is 1/6. Okay. Roll a dice twice, it goes up. And I can see the probabilities are going up. So I can take that, and I can plot it. Okay, so I'm going to take at least 1, and I'm going to scatter plot it, put roll on the x-axis, and here we go. Okay, so what do I notice? It is indeed true that as I increase the number of rolls, the probability of me getting at least 1/6 in my rolls goes up. And it goes up pretty quickly, right? So at like 20 rolls, once I roll a die 20 times, it seems almost certain, like I'm getting really, really close to 1, probability 1 that I get at least 1/6, which makes sense intuitively, right? You roll a die, the more times you roll it, chances are pretty good that you're going to get at least 1/6. All right, so let me take a look at that exact probability. Okay, so I have this table, at least 1. Let's say I'm really curious in seeing what the probability is at this point right here, the probability at 20 rolls. Okay, so at least 1 dot where roll is 20, and that gives me the probability. It's about 0.973, which is pretty high. Okay. Any questions about that? Excellent. All right. So this is the theoretical probability, right? So I use the rules of probability and said, OK, given that I assume the dice is fair, these are the actual exact probabilities of getting at least 1/6, because I use the rules of probability to calculate it precisely. The other way of finding probabilities is to just simulate. Okay, so what I did here is kind of like the power of math. I'm going to show you now the power of the computer. Okay, so what I'm going to do here is I'm going to say, OK, what is the chance of getting at least 1/6 in 20 rolls? Well, if I don't actually know anything about probability, I can just roll a die and try to find out that way, right? So let's say I get amnesia. I forget all my probability rules. I can still do computer simulations to try to figure out this probability. So what I'm going to do is I'm going to make a die. a die has 6 faces. I'm going to do from 1 to 7. Sorry. So here's my die faces. And to roll a die randomly in Python, I just do random.choice. Okay, so np.random.choice for my faces. Here I got a 6. Here I got a 4. Got a 3. Okay, and I can again put a comma here and say, OK, I want to roll a die 20 times. Here are 20 rolls. Okay, so here are my outcomes. Here are my outcomes. And I can see, OK, in this set of 20 rolls, did I get at least 1 6? It turns out that I did here. I can code that up in Python by just doing outcomes equals 6, get trues and falses, and then count how many there are, count non-zero. And there was 1 6 in 20 rolls. So it was almost 0, but I did get at least 1, so this does count as getting 1 6, right? So I could do this a bunch of times. So I just take that, run it. Here I got 4, take that, run it. Here I got 5, 2 6s, 5 6s, 3 6s. Maybe I'll get 0 one of these days. I have to run it quite. So you can see what I'm doing, right? I'm like running this a bunch of times. Ah, here we go. Here's a 0, right? I die a bunch of times, and I'm saying, OK, in every set of 20 rolls, how many times did I get 0? 0 6s. And I can use that to estimate the probability of getting at least 1 6. Right? So instead of doing probability, I just roll my die, see what actually happens in the real world, and then use that to figure out my probability. So I don't want to rerun that cell a bajillion times. So I'm going to write a for loop to do that for me. Okay, so I'm going to take my outcomes. I want to randomly generate outcomes. And for every outcome, I want to say, OK, how many 6s were there? If there was at least 1 6, so I can do greater than equals. I can do greater than 0. These two things are about the same. I'm going to do greater than equal to 1. So that's at least 1 6. So if I have at least 1 6, then I want to keep track of it somehow, right? So I have here, let's say I keep track of it in a variable called success equals 0. I'm going to say success. I'm going to increment it. So I'm going to take the old value of success and add 1 to it. Okay, so this says, I just kind of roll my dice. If I happen to get at least 1 6, I'm going to call that a success. If not, I'm not going to count it as a success. Okay? So I'm going to do this a bunch of times, which means that I'm going to say maybe like 1,000 times, do it 1,000 times. So I can stick that in the for loop. So for I in np.arange trial. So that says repeat this 1,000 times. And at the end of that for loop, so I roll my die 20 times, 1,000 times, right? I do 1,000 sets of 20. Figure out how many sets of 20 have at least 1 6. And then I can look at the probability by just taking success divided by trials. Because most of my rolls should have at least 1 6, but some of them won't. And that kind of like some do, some not, that lets me estimate the probability that I calculated exactly up here. So if I run that, I get 0.971, which is pretty close. Pretty close, right? So if I just increase the number of trials here, I can, in theory, get closer and closer to the actual value, actual probability. 976. OK, that's farther away. Maybe we can try again. 972. That's indeed very close. OK? So one way is to use math, right? We use the rules of probability to figure out this exact chance. The other way is to use simulation. And you look at this and you're like, OK, Sam, like, well, great job. You roll a dice like 1 bajillion times. I could have just done this in the very beginning and not do any of that. And that's very true. But sometimes the rules of probability are really, sometimes you get really complicated scenarios, and you won't be able to calculate this exactly. If you aren't able to calculate this exactly, basically your only option is to do the second one, right? So in the Monty Hall problem, a lot of us were not super clear on how the rules of probability exactly, like why they say the chance is better to switch. So I said, OK, I can just simulate it and see what happens. And then when we simulated it, we indeed found that it was better to switch. In this case, we indeed find that the probability of getting at least 1 6 is about 0.97. Okay, so if you ever take a probability class and you forget how to calculate a probability, you can just simulate it, put that down. I don't know if they'll take it, but you can try. Okay. So let me talk now about statistics. Okay, so this brings me to kind of one of the core themes in this class. So in data science, basically, the way that statistics was taught for a long time was that they said, OK, statistics is all about taking samples and like, using the samples to infer something about a population. And for a long time, they were like, OK, well, all students have our calculators. So we can't give them like really crazy data sets because they have to enter in all the numbers. We can't give them like, like weird data sets that contain strings and stuff because they don't know how to work with that. We'll just give them like simple data sets and kind of give them toy examples so they can work out the rules of statistics. Okay, that was the way they taught stats for maybe like the last, I don't know, 30, 40 years or so. And so, well, times have changed. And we sat down and we were like, or people in the department sat down and they were like, well, how will we teach stats now that people have computers? And that's kind of where the idea for this course came from, right? Because we have computers now, which means that we get to work with actual data sets that are really long, data sets that are really big, data sets that have different things about them, but more importantly, are connected to the real world, right? We looked at actual United flights. Okay, so that's the kind of motivation behind this class. And the reason why we teach stats is because first, we have the rules of probability, as I kind of mentioned before, right? The rules of probability say that suppose I know everything there is to know about the world, right? So I make some assumptions about the world. Given some assumptions, I can use the rules of probability to say, if I roll a die, I don't know, like 10,000 times, I should expect maybe like 1,600 of those rolls to be 3, right? So the rules of probability say, OK, given some assumptions about the world. So in there, my key assumption was that my die was fair, right? So if my die was not fair, I don't get to make any kinds of statements about whether or not I get however many 6s or 4s in 10,000 rolls, right? But here I'm making the assumption that my die is fair. The rules of probability then let me say, OK, so in the long run, you would expect this. Okay, so assume something about the world, and then say, from there, this is what the real world should behave like. Statistics, on the other hand, goes the opposite way, right? So in statistics, we say, I don't know much about the world, but I do know that I rolled my die like a million times, and I observe about 1/6 of those to be 3s. So given my observation, what I noticed in the real world, how do I go back from there to make judgments about how the real world is behaving, right? So probability goes from, OK, here's like the underlying mechanism. Here's how it should behave in the real world. Statistics goes, here's the real world. Let me find out the underlying mechanism by which things happen. Okay? And the two concepts are connected by sampling. Because in probability, I go from theory to real world by sampling out, by rolling my die and saying, OK, this matches my theory. In statistics, I take a sample and I say, OK, this probably came from some population, something in the real world. Let me figure it out. So so I'm kind of connecting all the ideas that we've talked about together. And in this class, and going forward for the next couple of weeks, we're going to be focusing very heavily on statistics, because this is more applicable to the real world. In the real world, oftentimes you're not going to get to make that many assumptions about the world, right? So for example, United flights, I look at United flights and I'm like, OK, what assumptions can I make about that? Not that many. I don't really know what they look like, But with statistics, you can eventually say, OK, I don't know my entire population. I only know like this small subset of that. So if I have like 1 million people, I want to know how many of them, I don't know, like what have water bottles. I can't go to every 1 million people, all the people in that 1 million group, and figure out how many of them have water bottles. But I can maybe look at 100. Okay? And with that small group of 100, I can actually go back to that million and say, I can actually say, OK, it looks like probably around this many people will actually like water bottles. Okay? So that's the power of statistics, and I hope that it will be clear to you why stats is useful in the weeks coming, because it'll start to get pretty complicated and pretty nuanced. I want to brace you for that and get you excited now, because in about a week's time you're going to be like, what is hypothesis testing? Okay, so let's talk about estimation. Okay, so at the heart of stats is statistical inference. Okay, so as I said, I want to make some conclusion based on that random sample, even though it's not my entire population. Inference allows me to do that. For example, I can use my data to guess the value of a random number. So for example, the percentage of people that like water bottles, or a percentage of flights that were maybe like 20 minutes late or more. Okay. And what I'm going to do there is create an estimate of what I want to figure out. So my assumptions here are that this unknown number is fixed. Okay, so for example, in my dice roll, let's suppose I'm trying to estimate the probability of getting at least 1/6. Okay, I'm going to assume that that probability is fixed, as it doesn't change between dice rolls. It stays the same as whatever it was before. And my estimate here depends on my random sample. So I roll my die. I say, oh, OK, I roll my die 1,000 sets of 20. Of those 1,000 sets of 20, maybe like 10 of those didn't have 6s. That's my random sample. And given my random sample, I can use that to estimate the quantity that I want to estimate, which is the actual real probability. Okay. So let me take a look. Okay. So that random quantity usually has some names. So first of all, I want to give you some vocabulary. A parameter is what we say is a number associated with the population. Okay. So given my entire group, the parameter is like the real underlying value that we're usually trying to figure out, right? So number of people that like fancy socks, right? So an actual population value. Okay. A statistic is a number from my sample. Okay. So in the real world, there may be like some number of people that like fancy socks, but I don't get to look at all the people. I can only look at maybe 100 of them, maybe us in this class. The sample is how many people in our sample like fancy socks. Okay. What's key about this is that I can use a statistic as an estimate of a parameter. Okay. I'm going to show you how that works. So in my dice rolling, I noticed that I got, let's go back to 1,000 because that runs faster. I noticed that I get 0.983, right, which is like kind of maybe 0.983, like maybe like 1% above. Or do it again, maybe 968, right? I guess so this is not always accurate, right? And it's not always accurate because there's random chance involved. I could get a little bit below the real probability. I could get a little bit above. How like varied is this estimation, right? I want to know how accurate this estimation really is. So what I can do is I can just take this and say, OK, well, I got 973 this time, which is actually really accurate. But how likely is it that I'm going to actually get something close to my real number? What I can do is I can get a bunch of these numbers and see their distribution, right? So instead of running this over and over again and looking at all the numbers and saying, OK, it looks like I'm getting about 9.96, 0.98, I can just run this multiple times and look at that distribution. So what I'm going to do is take this and put it into a function so I can run it a bunch of times. So I'm going to say trials is instead a parameter in my function. So here is trials. Put that on the function. Okay. And now I can just do roll 20. So I didn't do anything special there except just move stuff around. I can now do roll 20 with 1,000. And this is exactly the same as running this cell up here, except now I can just call this function. Okay, so I do that. And I need to return. Forgot to return. There's 0.974. Okay, so I can do that. So now I want to do this a bunch of times. So I can do another for loop. Okay, so I'm going to do for I in np.arange. Let's say I want to do 1,000 of these estimates. Do that, and then I can say, OK, I have a table of estimates. And I'm going to say, put that in my table. Estimates.append. Roll 20. So it's not super important to understand this code. Just understand what I'm trying to do here, which is do my simulation, get my estimate for the probability, and just do that a bunch of times. Get a bunch of probabilities. See whether my probabilities are accurate or not. Okay, so do that. And now my estimates table looks like this. I'm going to clunk along. This is about 20 million dice rolls, so it's going to take its time. So, estimates. And hopefully I didn't crash the servers. Come on. You can do this. Let's go, Python. Puzzling. Maybe I shouldn't run it with this many rows. OK, well, I'm going to try kernel and then interrupt. Oh, OK, so it was starting. Maybe I'll do maybe I'll do 100, or maybe 500 instead of 1,000. 200. 200. Let's try 200. Okay. Let's try that. It'll chug along. And I should get a table of probability. Oh, there we go. So we have a table of probabilities, right? So I just ran my simulation over and over again. Here are my estimates for the probability of getting at least 1/6, right? So I have a bunch of these guys. I can draw a distribution of these. So I could do a bar chart just to show you every single possible value, bar H. Here I see, OK, I got like 0.968 here. So here's my actual value, like 0.974, which looks like it was pretty likely. It looks like 0.976 happened, and 0.978 happened, and it kind of goes down like that. But it looks like overall, like the shape of this is kind of centered at the actual value of my probability, right? 0.97, I think it was 0.9739, which is about 0.974. It's better to look at this in a histogram, of course. So I'm going to look at it in a histogram. Here we go. Okay, so it's kind of going up and down. Now, if I did more trials, it would look more smooth. In this case, you can still see that this is centered at about 0.974, which is about right here. Okay. Any questions about that? Yeah, Sean?
Just general question, like intuitively, I mean, are we basically writing these programs based off the law of probability, and then we're given in that law of probability the program, like we're making up for error? So we're just telling the program, as long as you keep continuing to run the program over and over again, you're going to erase some of the error. So
Yeah. So that's kind of a good way of thinking about it. So we said, OK, the die is fair. That's my law of probability. That's like my assumption. Based on that, I can say, OK, take some random rolls. And even though there's going to be some random variation, in the long run, I should get back my original value. Yeah. OK, so there's a die. I think you guys are getting tired of dies. Let's talk about planes. Okay, so first I'm going to do attendance. All right, resume. And here's a link. All right, how many of you guys are sitting in row D? Row D, my dears. OK. How many of you guys are sitting in row G? OK. What about column number 4? Column number 4. 4, yes, excellent. 1, 2, 3, 4, count up. OK, column number 7. Number 7. OK. Make sure you know where you are. I only see Alan raising his hand. I hope you guys know where you are. OK, so let's talk about estimation. So before I was estimating probability, but here's an actual example. So in World War II, the Allied forces were trying to figure out how many planes the Germans had, right? And what they saw was that when the German planes flew overhead, there was like a serial number kind of stamped to the plane somewhere. So maybe like on the bottom here. And what they would do is they would take a picture or like write down the number of that plane, and they'll try to figure out how many planes the Germans had in total. Right? So if the Germans only had like 100 planes, the serial number should only go between 1 and 100. If the Germans had 30,000 planes, the serial number should only go between 1 and 30,000. Right? So that's kind of their basic premise. They're trying to figure out how many planes the Germans had so they can figure out how to fight better. So here are my assumptions. Okay? So the planes are numbered from 1 to n. So not any like random numbers getting inserted in there. They're numbered sequentially. And we don't know n. I want to figure out n based on what I observe. Okay, so in this case, so before we're talking about going from probability into the real world, right? So knowing what the real world is and then seeing what happens. In this case, I don't know how many planes the Germans had. I want to figure it out based on what I observe. Okay, and my main assumption is that the planes that I see are a uniform random sample drawn with replacement. This is important because now I can say, OK, it's equally likely that I see any plane. This lets me actually do statistics. Okay, so let me ask you a question. If I saw these serial numbers, what will my estimate of n be? The estimate of the number of planes the Germans had. Talk to your neighbor about it. I don't hear much talking. Go ahead and talk to your neighbor. What do you think your estimate of n would be? What do you think is most reasonable given what you see here?
Yeah, something like that. It can be below 2. Yeah, 291.
So you know that there's at least 2 variables.
All right, what are your guesses? Can I just hear some numbers? Kevin.
300.
300 planes. Why'd you pick 300?
Actually, around 295 to 305.
Okay, so Kevin says around 295 to 305. Okay, any other guesses, Ilian? 291? Oh, okay, so you're saying, okay, so it definitely cannot be less than 291. 291 seems pretty safe. Aubrey? Andy, sorry. My bad.
350.
150, why do you say that, Andy?
Because we see we don't have a lot of numbers in the hundreds, so we can assume that these are maybe skewed more towards the 200s. So there could be some higher than that, but not many.
Yeah, so Andy, you're saying, it looks like we don't have a lot of 100. So it seems like we're getting higher numbers, which says maybe my actual number is higher. Okay, so all great guesses. So in particular, this 291 here is a pretty safe guess, right? So if I have my sample, I know for sure that the number is not less than 291, right? So there's at least 291 warplanes. So maybe we'll go with that as our first guess. Just go with the largest number of my estimates. Okay, so let's see what happens. I'm going to spoil the surprise for you. Oops. Okay. Okay, so I'm supposed to do this slide. Okay, so we're going to say, okay, let's go with the largest one, but then we have some questions, right? So maybe it's actually 300, maybe it's more than 300. How good is this estimate of always going with my largest plane? Okay, so I'm going to ask the questions. If I look at my sample and just take the largest serial number and say that's how many planes the Germans have, how likely is it to actually be the actual number n? Or how close is it going to get? If it gets close enough, maybe that's good enough for my purposes, right? So option number 1 is using the rules of probability and saying, okay, find a probability of getting my sample and then trying to infer from there the actual n. Seems kind of complicated. So in this case, I'm just going to simulate, draw an empirical histogram, and see what happens. Okay. All right, so let me do my demo. Anyone still taking attendance? Very well. Closed. And here's my notebook. All right, so here I have, it's a table containing my planes. I'm going to spoil the surprise for you. There are actually 300 planes. Good job to you guys who thought 300. But you guys got pretty close. There are actually 300 planes. You guys all guessed around 300. No, like 1,000, which is good. Okay, you guys are thinking. Great, so I have the numbers 1 through 300. These are the actual planes that I could possibly see, right? So all the planes I could possibly see. And what I'm going to do is I'm going to take a sample, right? So just sampling out of this table lets me say, OK, I observed these plane numbers. Okay, so I'm going to take my sample, serial number, sample, and let's say I have a sample of 30 out of this table. So I observed 30 planes. Here are the numbers that I observe. So they're like that. If I take that column and I want to find the maximum, I'm going to take the column, the first column, or 0th column, and then take the max of that. Here is my estimate of n. And in fact, this time it got quite close. 299 is pretty sweet. Okay, I run again, 293. Okay, also pretty close. So I run that again. Oh, OK, it looks pretty good, right? Mostly in the high 200s. Here's my n, right? Mostly in the high 200s. So you can see it, taking the max of my sample actually gets me pretty close to the value of n. But how close? Well, to actually figure out, you have to draw the distribution. And to do that, I'll just do this a bunch of times. But instead of running the cell over and over again, I'll use a for loop. Okay, so let me do a for loop. How many repetitions do I want? Maybe like 1,000 for I in np.a range. I'm just going to say repetitions is 1,000. Repeat this 1,000 times. Okay. And this sample size, maybe I'll keep it at 30. I'm just going to put it in a variable so it's easy to understand what the 30 comes from. Typically, I like to put these numbers in variables. Oops, I should put that there. Repetition. I like to use variables here instead of actual numbers, just because I look at this later on and I can say, oh, OK, this is actually how many times I'm repeating. This is my sample size, right? So it's a little bit more descriptive to me than just straight up numbers. So I'm going to do that, sample size 30, and then use sample size here. So a little bit more verbose, but more clear to me when I look at it, what it's doing. Okay, so I'm going to do that, take a bunch of estimates, and I need to keep track of those estimates, right? Because if I don't save the estimates anywhere, it's going to get thrown away by Python. I'm just going to put it into an array. So here is my maxes. I'm going to make array. Here's an empty array. I'm going to say my maxes equals mp.append. Take my old maxes and put in the new estimate. So here is my sampled n. I'm going to put in my sampled n. So if I look at my maxes now, maxes, I have a bunch of estimates. I just did 1,000 estimations, right? So I observe a bunch of planes, right? So I observe 30 planes 1,000 times, and I make estimates based on that. So here, OK, this time I said, OK, 295, this is 260, 299. Here's my array. I'm going to put that into a table instead of an array. So estimates, table with columns. I'm going to call this my max serial number. And put my maxes in there. Okay. Now I have this estimates table. Wow, 2 300s in a row. Amazing. Okay, so I'm going to say make a histogram. And I get that. Not super clear what's happening. Let me just change the bins. And bins equals mp.a range, maybe from 1 to 400, incrementing by 10. I have this kind of wide histogram here. I can see that, in fact, taking the max of my sample is pretty good, right? It gets me like pretty close to my value of n. So what that means for me is that if I go back to this previous slide, so I had this slide, and I said, OK, I only have this one sample. In this particular case, I had the advantage of being able to take as many samples as I wanted, right? So I can take as many samples as I want and look at all the samples and say, oh, OK, looks like my max is pretty close. But if I only had one sample and I took the max, what this tells me is that even if I only have one sample and take the max of that one sample, chances are pretty good that it'll be close to n, right? Pretty close to n. Now, not exactly n, right? Because if you look at this, this will always, more likely than not, underestimate n by a little bit, right? If you look at these numbers, none of them go above 300, and some of them go below 300. So that means that on average, my estimate will be probably a little bit below n. It looks like on average maybe like around 290 or 280. So it will be pretty accurate, but not exact. Not exact. Any questions about what was done here, Kevin?
It's a little bit of an off-tangent, like conceptual question, but above when you put in the sample size versus the sorry, could you go up a little bit?
Yeah, here.
Yeah, the repetitions and the sample size. Could you say a little bit about the relationship? Like if we switch that and the sample size is 1,000, repetition 30, which one has a bigger effect on getting closer to the truth?
What a great question. So Kevin's saying, what happens if I made a mistake and I switched these two? So I said this was 1,000 and this was 30. That's a question I think I'll leave for you. Try it out. See what you find. OK. Those are the kind of questions you should be asking. Those kind of questions where you're like, what if I do this? What if I do that? Those are the things you really want to explore, because those kind of questions are what will actually give you a sense of intuition for what's going on here. Okay, so try it out. OK, so I've gotten this, and I've said, OK, pretty close, pretty close. So go back here. So largest number observed. Let me do what I think this looks like. OK, oops. So yes, we think that if I take my sample, take the max, chances are pretty good that it'll be close. It seems to be like a reasonable estimation of n, right? But it'll also be lower than n most of the time. So a little bit off, right? It's not particularly like exact. So maybe I can do, instead of taking the max of my sample, I can take the average of my serial numbers and multiply it by 2. So the intuition behind that one is, let's say the numbers came between 0 and 100, right? So if I took a bunch of planes and I looked at the numbers, chances are more likely than not that the average of those planes will be somewhere around 50, right? So if the planes go from 0 to 100, observe some planes, look at the numbers, take the average. The average should be around 50, because that's like the middle point of all the plane numbers. And then if I multiply that 50 by 2, I should get something close to the actual number of planes, which is 100. Right? So it's not too hard to try, so let's try it out. So my new estimate is 2 times the average. Let's see what it looks like. Okay. So it's actually quite easy to add that. All I really need to do is paste that here. And say, OK, I'm going to keep track of both the max and twice the average. So let me pull this up. OK, so I'm going to call this doubles, make a new array. So here I've done the maxes. I can also just add something to the doubles. I'm going to say keep track of the max of every sample, but also keep track of the average, 2 times the average. So add average of my sample then. Okay, so here, so I have to be careful here because I did the max here. I don't want to do the max here. I just want to take the sample. So this is my sample. And then I want to do np.max of my sample. I'm doing the max of my sample, and I'm also going to do the average of my sample times 2. Okay, so one sample, take the max, take the average, multiplied by 2. I get 2 estimates for every sample, so I can compare which one was better. So I run that, make sure to put that in my table. So 2 times the average. Put my doubles in there. Run that, and it broke. Sample is not defined. Misspelled it. Okay, so here we go. I have my sample. This is sample number 1. In sample number 1, the biggest number was 298. And 2 times the average was 317. So it's a little bit overestimating this case. Let's draw a histogram and see what they look like. Estimates.hist. I'm going to use the same bins. My bins there. Okay, so what do we notice? Okay, so we notice that the max serial number is like pretty narrow, right? And 2 times the average is pretty wide, but it looks like 2 times the average is centered at 300. So it looks like on average, 2 times the average. So if I take a bunch of samples, doing the estimation of 2 times the average will actually get me 300 in the long run. It will actually get me the value of n, but with some cost, right? It's kind of flatter, more spread out. Whereas if I do the max, it looks like it's more narrow, so my estimates are not going to be as varied, but it's going to be a little bit under 300. I'm going to underestimate a little bit. Okay. So I'll leave you to think to that over our break, and let me go to the education idea of the week. So that's all for content for this first hour. I'm going to leave you with this idea and then give you a break. Okay. So this week, my education idea is called the law of the broken futon. How many of you guys have heard of the law of the broken futon? No one, because it's not really a law, some guy just made it up, but I thought it was pretty clever, so here we go. Okay, so if you want to look at the blog post about it, you can click on this. But basically, the story is, this guy, let's call him Matt, okay, and his roommate Dave. Okay, so Matt and Dave went to IKEA and they bought a futon. And they were assembling the futon, and they were like, well, it looks like we're missing a piece. What could go wrong? Let's just assemble the futon, right? So they assembled the futon, they're missing that one piece. It looked like it was fine, right? Just sitting on it, pretty happy. And then they noticed that the futon started to sag a little bit in the middle. And they're like, well, it seems OK. We can keep sitting on it, right? We're still sittable. And then, well, at some point, it got kind of unsittable because they kept sitting on it. And they got kind of smashed together. So here's Matt and Dave. And then, at some point, the futon just snaps in half because they're missing that important part. Futon's missing a piece. And he looked at that and he was like, seems like a metaphor for life. And so what he said was, OK, well, let's suppose that you're learning math in school. And you're like, wow, like functions, equations, I can do all that. So I can take a line, find the slope of the line, like x equals to 2, y equals to 3, all of that I can do. But if you're missing some like foundational, some really important concepts, right? Let's suppose you don't really understand that an equation is like, so for example, in this case, an equation is a set of points that fulfill the condition y equals to something times x, right? It's a set of points that fulfill that condition. If you don't really understand that core mathematical concept, then you're going to have a lot of trouble when it comes to like, I don't know, sinusoids, when it comes to taking the limit, when it comes to doing parabolas, right? So you can do all of this just fine, right? Even if you miss some piece or miss some important pieces, chances are like at the time being, you can still like, oh, okay, feels pretty good. My futon, holding together. But then you notice your futon starts to sag, and as you go farther and farther along, your futon like kind of starts to sag more and more until one day it just breaks in half. And what he said was, well, so he's a math teacher, and he was like, well, I teach math, and I notice that people often feel like they reach their mathematical like breaking point, right? So they're like, there is some limit at which like my math knowledge, I cannot advance any further. This is the end for me, right? And what he noticed is that, well, chances are that it's not, you haven't actually reached your limits. He says chances are you're probably just missing a foundational piece in your knowledge, right? That seems more likely than like you kind of reaching your limit at the tender young age of like 16, And so he was like, well, it seems like chances are you probably just missed some foundational piece. And if you're missing some foundational piece, you're kind of like a student with an expiration date, unfortunately, right? Because at some point along, your futon's going to break, and you're going to think, I can't do this. I'm not cut out for it. This is not for me. This student will never get trig. The student will struggle with, I can't read that. Won't understand derivatives. Will hate pre-calculus, right? And his point was basically, well, okay, so there's a lot of the broken futon. His point was basically, if you're missing foundational pieces in your knowledge, and you try to move on, at some point, life is going to be hard, right? Eventually, your futon collapses. And unfortunately, the way the school system is structured now is that we all sit in the classroom together, with me, of course. We all sit in the classroom together, and we try to learn the same pace, right? So I lecture along, and I lecture at the same material to all 100 of you, or all 70 of you guys. And unfortunately, that's just the way it's structured today. And what happens is that some students like get it or like spend the time and really understand the concept, and some students don't. But the students that don't take the time to really understand like a really important foundational piece in their learning have to move on because the classroom just moves on without them. And if you miss that foundational piece, at some point your futon is going to collapse. And people have been thinking about for a long time ways to kind of address that, right? So if you're familiar with Sal Khan and his ideas about the flipped classroom or like mastery-based learning, all that stuff is trying to address that one very core limitation of like this particular style of classroom. But the reality is, I'm here lecturing, and you're here listening to me. All 75 of you are listening to me. And it looks like, at least for the time being, you guys are going to be stuck with me, lecturing to all of you the same thing, right? And so my suggestion to you is, well, given that we can't change our educational system overnight, as students, we can try to figure out how to best address that. And to me, the best way to address that is by really sitting down and reflecting on what you learn, right? So self-reflection, thinking to yourself, okay, I feel good about this. I don't feel so good about that, right? And being able to articulate exactly what it is that you're having trouble with. Okay, I'm having trouble with stats, but not just stats. I'm having trouble with like this particular idea of sampling, right? I understand like this particular sampling scheme, but not this particular sampling scheme. Being able to point out exactly what it is so that when you get help for it, or when you come to us in office hours or ask me about it, you can actually say, okay, I need help in this. I need help in X, Y, and Z. I feel shaky about stats overall, but I think these are my most important issues. That's the way you can make the most out of your time, make the most out of our time, and hopefully we can help you guys learn. Okay, so I wish we could change the educational system. But this is our reality, as the Bart Twitter so eloquently put it. So we'll try to make do with the best we can. And I and the rest of the core staff will do our best to try to help you guys out, help you not to break your futon. Okay, so let me ask you a question, which is, what is the missing piece in your knowledge? So time for you to do some self-reflection while we take a 5-minute break. Go ahead.
Here's my problem with the homework submissions. I can ask you right now.
Sure. Hold on. So we'll start again at, let's say, 11. What time is it now? 11. We'll start again at 11:14. Start at like 11:09. 11:14. Okay.
I noticed something like